This is Lab 3, Orbit Around a Black Hole. The objective of this lab was to determine the mass of an imaginary black hole, based on the motion of a star orbiting the black hole. I found the mass to be about 5.17 times 10 to the 31 kilograms, a sensible result based on the size of the star. The orbit of the star around the black hole uses the principles determined by Newton. In our system, we have a black hole interacting with a star of mass 3.9211 times 10 to the 27th kilogram, creating a gravitational force between the two. In order to determine the force of gravity, we must use the law of universal gravitation, or F net equals big G times m1 times m2 over r squared, where G is the gravity constant, m1 and m2 are the mass of the two objects in the system. In this case, m1 is the star, m2 is the black hole, and r is the magnitude of the distance between the two objects. From our code, we are able to get the net force based on the change in momentum, since dP equals dt. Using Newton's second law, we are able to determine from the given star positions the velocity and acceleration. And from the momentum principle, P equals mv, we can get momentum. To determine if our model was a good fit for this system, I had the code calculate the mass of the black hole at each time step. Although the mass fluctuated some, there was only about a 2% maximum difference between the calculated mass and the actual mass. This shows the code almost perfectly predicts the mass of the black hole and is a good fit. Based on our universal gravity equation, we know the star's mass and gravity constant remain unchanged. So only a fluctuation in the star's change in position between each time accounts for this. If the change in position and therefore change in net force occurs, the calculated mass is also subject to change. In addition to an accurate mass, we must also make sure the model's motion fits the actual motion. As we can see, the star is moving with a curving motion, with the black arrow representing the parallel force, the blue representing the perpendicular force, and the yellow representing the average net force. Another component to point out is that in this lab we repeatedly set dP dt equal to F net. But are they actually the same? The answer is no. When we calculate it, we see they numerically equal each other. F net equals ma, A equals delta V, therefore F net equals m times delta V. We can see here that delta P over delta T also equals mass times change in velocity over change in time. However, they do differ conceptually. For example, we can calculate dP dt in the perpendicular or parallel direction to an object's motion, but we can truly only observe the parallel and perpendicular force. This allows for us to assume dP dt and F net are the same, but when we dive deeper, we see they are actually not the same at all. Another question that may appear is if the black hole was replaced by another black hole, since we cannot see these and therefore cannot observe this, would the mass change if the star's motion remained the same? The answer, again, is no. We can look at our universal gravitation equation again to understand this. The gravity constant, g, and the mass of the star stay the same because g is a constant, and the star's mass is constant also. And the motion, so position stays the same, then r here does not change, and neither does force. Based on these results, it would be impossible for the black hole's mass to change. This could only happen if the star's position or motion was to change.